I'm going to speak about a paper with Mikola Matvichuk and Travis Shedler. It's been on the archive for a little while, but there was a significant update which came out about 8 months after the first version, where we removed some technical hypotheses. Nevertheless, for today, I'm mostly going to work with those hypotheses in place because it simplifies the exposition quite a lot. All right, so this is about log symplectic manifolds. Log symplectic manifolds are generalizations of holomorphic symplectic manifolds. So they're closely related to hyperkähler manifolds. For instance, you may get them by trying to compactify a hyperkähler manifold, or by taking a hyperkähler manifold and degenerating it to get something normal crossings, and then typically the irreducible components of the degeneration will carry a log symplectic structure, as explained by Harker. So what is a log symplectic manifold? It's a triple, x, d, and omega, where x is a complex manifold, d inside of x is a hypersurface, a complex hypersurface. I'm not going to make any assumptions. It could be singular. It may be reducible. And then omega is a holomorphic two-form on the complement of this hypersurface, which satisfies some hypotheses. So first of all, it defines a holomorphic symplectic structure in the interior, x minus d, which means in particular that omega is closed. So d omega is equal to 0 in omega 3. The log part comes by requiring that omega has first order poles on D. And then, as usual in symplectic geometry, there's a non-degeneracy condition on the two-form. In the absence of the divisors, just a statement that the top exterior power of the two-form is non-vanishing. I should say here that the dimension is always even. So in the logarithmic context, we require that the top power of omega, which is now a section of the canonical bundle of x having first order pole on the divisor, this has to be non-vanishing. Okay, so it's a straightforward generalization of the notion of a holomorphic symplectic manifold.
So the second condition, first order pole, that doesn't sound like completely equivalent to being logarithmic, right?
But it's close, so it actually is equivalent.
But if you require it's logarithmic, then the third condition is perhaps superfluous, isn't it?
The non-vanishing part is not superfluous. The fact that it has a first order pole follows from the logarithmic condition, but the non-vanishing is not superfluous. So I phrase things slightly differently. Instead of talking about the log forms, but it's equivalent to saying that it's a non-degenerate log form. Okay. So I'm going to give some examples, but first let me observe some important consequences of the definition. Okay. So the first thing, which is probably the most obvious, is that this divisor D has to be an anticanonical divisor. And it's even a reduced anticanonical. Okay. So I said the singularities could be arbitrary, but I don't want the thing to be non-reduced. Okay. Thanks. Okay, the second thing is that because the two-form is non-degenerate, I can invert it in the interior to get a bivector. And these conditions actually imply that this bivector extends to be smooth on all of x. So let me call that pi. It's a global section of wedge 2 of the tangent bundle of x, and it has a few additional properties. For instance, pi is tangent to the divisor, and the condition that d omega is equal to 0 corresponds to the statement that the bracket of pi with itself, which is a trivector, is 0. So maybe this is not so familiar, but on the exterior powers of the tangent bundle, there's a bracket called the Schouten bracket, which is a generalization of the Lie bracket of vector fields. Okay. And as a consequence, you can define an operation on the functions. If I take a pair of functions, then I can take their differentials and pair them with this bivector, and that will give me a new function. And this defines a Poisson bracket. So remember, on any symplectic manifold, the sheaf of functions carries a Poisson bracket. And the claim is that this Poisson bracket extends to the manifold X in such a way that this divisor is a Poisson subset. Okay, and as a consequence of the Poisson bracket, every function has a Hamiltonian vector field, Cf, which is the derivation given by bracketing with f, or equivalently the contraction of df into the bivector pi, which is a vector. Okay, and these generate a foliation of x. So it gives a decomposition of X as a disjoint union of some immersed submanifolds Li, and each one of these submanifolds is itself a symplectic manifold. So what I can do is I can take the bivector and I can restrict it to the leaf, Li. There it becomes a non-degenerate bivector on the leaf, and then I can invert it again to get a 2 form. Okay. And so this is a holomorphic symplectic form on this leaf. Okay, so a log symplectic manifold is actually a whole pile of holomorphic symplectic manifolds that have been stuck together. Okay, so examples. First example, let's take the dimension of x equal to 2, and then the condition that d omega is equal to 0 is vacuous. And equivalently, we can say that this pi is a section of the anti-canonical bundle, which is vanishing to first order on the divisor. So I have a surface with a section of the anti-canonical bundle. D is the vanishing set of pi, and the leaves, what do they look like? So first of all, there's an easy leaf, which is the complement of D. That's always an open leaf in this foliation. So in this case, it will be 2-dimensional. And then, at every point in D, this bivector is vanishing, which means also that all of the Hamiltonian vector fields are vanishing. And so given that they're generating the foliation, but they're vanishing at this point, it means the foliation just consists of a bunch of points, all the individual points of D. So points of D. These are leaves of dimension 0. Okay, so the typical example would be x is P2, and then the divisor is a cubic. So if the cubic is smooth, picture something like this. Okay. So I have the open leaf, which is the complement of the cubic, and then the individual points on this elliptic curve are the 0-dimensional leaves. Okay. But I'm also allowed some singularities. So for instance, I could take this smooth curve and degenerate it to a triangle of lines. That would be okay. I could also degenerate it to a cusp. That's allowed. What's not allowed would be something like a line taken with multiplicity 3.
So is there some property like that the cuspidal one doesn't satisfy that like the normal crossings ones would, or is there any sense in which that one is less nice than the other two? Or?
Pick your favorite reason why
Yeah, okay,
the
right,
cusp
okay,
is
yeah.
worse than the normal cross.
There's nothing that shows up in like the...
Nothing so far in what I've said, but later on I'm going to talk about deformation theory, and then things are going to get much more complicated if we don't impose some kind of hypotheses. Okay, now it's my turn to demonstrate my competence. I like this system so much, actually, that I installed it in my own office at McGill. However, it's always more frightening to do it in public. Okay, what about higher dimensional examples? So maybe the easiest thing to do is to take X to be a smooth toric variety of dimension 2n, and take D to be the toric boundary, which is always a simple normal crossings divisor. And now I can do something very simple. Okay, so let me take coordinates on the torus here. And then I can simply take omega to be a sum of terms where I take dxi divided by xi, which dxj divided by xj. So this has a pole of order 1 when xi or xj is equal to 0. And these bij's are just a skew-symmetric matrix of constants. So it's just an invertible skew matrix. Very simple. So what does the foliation look like in this case? Well, always there's the open leaf, which is, in this case, just the torus itself. And then the toric boundary consists of a bunch of subtori, which have been subbed together. But there are some tori which are even dimensional, there are some which are odd dimensional. The odd dimensional ones can't possibly be a leaf because symplectic manifolds are even dimensional and all the leaves are symplectic. So what ends up happening is that you get a stratification by these subtori, and then each one of these tori itself has a foliation, which may not even be algebraic. So the leaves of the foliation can be transcendental submanifolds. It's very similar to this famous example where you take R2 mod Z2 and you look at the orbits of translation in an irrational direction. And they end up being dense in the compact 2 torus. Okay? So there's a kind of holomorphic counterpart of that picture, which can occur depending on what these constants Bij look like. So the foliation can be interesting. Okay. An important class of examples come from various moduli spaces. Sheaves, bundles, etc. So, for instance, if you take the Hilbert scheme of points on a log symplectic surface, this carries a log symplectic structure. In the symplectic case that was explained, for instance, in the work of both Veal and Mukai, and generalized to actually any Poisson surface by Tautet-Chin. But there wasn't actually a lot of work done about the Poisson geometry of these manifolds. So Nicola Travis and I wrote a paper recently where we explained what the symplectic leaves look like, and how the deformation theory of these manifolds looked, and so on. That's not the topic of today's talk. But basically the idea is that the symplectic leaves in the Hilbert scheme come from sort of taking products of this picture, right? So here I can have points in the open leaf moving around, but then one of them may end up approaching the divisor, okay? And once it gets there, it's kind of stuck. It isn't allowed to move to a different point on the divisor. So another example of a leaf would be to choose a point on the divisor and let the rest of them move around in the open part. And then it gets more complicated when points start colliding along the divisor. So it's essentially the intersection of a zero-dimensional subscheme with the divisor, which controls a symplectic leaf, but it's not the ordinary intersection, it's the derived intersection.
Okay. For more general moduli spaces, do you ever get this kind of weird foliation structure?
So typically what happens when you have something coming from a moduli space in algebraic geometry is that all of the symplectic leaves have a modular interpretation, and therefore they're also algebraic. Okay, so other examples, certain moduli spaces of bundles on elliptic curves are known to carry Poisson structures, thanks to work of Fagan and Odesky. And if you tune the degree and the rank of a bundle, then you can arrange this thing to be log symplectic. The moduli space of SU2 monopoles is a non-compact hypercalar manifold, but it has a log symplectic compactification. It was explained by Tia and Hitchin. And the A compactification was discussed by Goto. Okay, there are many other examples. So in fact, the character varieties that we heard about earlier this morning often have log symplectic compactifications. And that, I think, is playing an important role in this Peoples W story. Okay. So I want to say first a little bit about the local structure of log symplectic manifolds, which I'll return to in a little bit more detail later in the talk. But let's begin by recalling that if you have a point in a symplectic manifold, remember the complement of D is an honest holomorphic symplectic manifold. If you have a point in a symplectic manifold, then one of the first things you learn is that this point has a standard neighborhood given by the Darboux theorem. So there's a holomorphic version of Darboux's theorem, which says that there exists holomorphic coordinates such that omega looks like the sum dx1 wedge dy1 plus dot dot plus dxn wedge dyn for some holomorphic coordinates x and y. Okay. So the mantra in symplectic geometry is that symplectic manifolds have no local invariance. They always look the same in a neighborhood of any point. Okay. Now what's happening at a point on the divisor? Well, let's start by looking at a smooth point. So at a smooth point, actually it turns out that there's a version of the Darboux theorem, which you might call the log Darboux theorem. And it gives me almost the same answer. It says that omega looks as follows. So first of all, I'm at a smooth point, so I may as well assume that D is cut out by the vanishing of one of the coordinates, say x1. Okay? And now I'm allowed to have a pole of order 1 when x1 vanishes. Okay? But otherwise, I'm going to do exactly what I did before. So the only difference is this, this pole here, and in particular you observe something, which is that omega somehow splits apart as a product of something which is just honestly symplectic in 2 less dimensions, and this kind of surface.
Sorry, I should have asked before. Are moduli spaces on log symplectic? Moduli spaces of sheaves on log symplectic surfaces okay too? Or?
They're Poisson. Whether or not they satisfy the non-degeneracy condition, I don't know off the top of my head. But presumably, for at least for certain numerical invariants, they will. Okay, so now the obvious next question is what happens when we're at a singular point of the divisor? Okay. And well, things get complicated. And we really don't have much in the way of a local classification. What's definitely true is that you can see any plane curve singularity in codimension 2. But in codimension 3, there are constraints on which singularities can occur. Okay, so that's just for D itself. And then there's a separate question, once you fix the singularities of the hypersurface, what can the symplectic form look like? And in general, there will be parameters in the local normal form for Holoc.
Which kind of constraint you have in codimension 3?
So what is true, which I proved with Gualtieri, is that every irreducible component of the singular locus has codimension at most 3. And if the codimension is exactly equal to 3, it has to be a Gorenstein scheme. That's already some strong constraints, but that still leaves a lot of room. And actually the closedness of the 2 form imposes further constraints, which I don't really know how to explain it in more classical algebraic terms. Okay, so one thing that's interesting is that if you're in dimension 4 or greater, you can't possibly have an isolated singularity of this hypersurface. The singularity locus has to be quite big. Another complication, okay, you have a singular hypersurface, your instinct is to resolve the singularities by blowing up. Okay? But you're going to get yourself into trouble doing that, because if you take a Poisson manifold and you take a submanifold, you blow it up, the Poisson structure typically gets destroyed. It will develop poles along the exceptional divisor. And that definitely occurs for these log symplectic manifolds. However, there have been some recent developments in resolution of singularities, which I think will be discussed a little bit tomorrow afternoon, using weighted blowups. And with a summer student, Simon Lapointe, Nicola and I were able to see that actually using weighted blowups considerably improves the situation. So there are lots of log symplectic structures which you cannot resolve with an ordinary blowup, but you can using a weighted blowup. Okay, so anyway, the message is that the singularities are a bit hard to manage.
So excuse me, maybe this is naive, but if you just say Pn with the Torelli boundary, then you get something very bad at like 1, 0, 0, 0, right? It's not just codimension 2 or 3. So you, because you have big...
Yeah, so I said the irreducible components of the singular locus.
Okay.
But you can certainly have strata of higher codimension.
Okay,
But
so you just
but there in the toric boundary, you have the double intersections of divisor components, which are codimension 2. That's where the singularities start.
Okay, so that's...
Okay, so what I want to discuss a little bit about today is trying to get a bit of a handle on the classification of these manifolds. And in particular, I want to discuss the moduli space. So let's consider M, which is going to be the moduli space of log symplectic manifolds up to isomorphism. And, well, in light of what we said earlier, we can situate it in the broader context of holomorphic quasi-manifolds, which is going to be useful in a little while. But what I can say is that there's very little known about the moduli space of holomorphic quasi-manifolds outside the compact hyperkähler case, which has, of course, been subject of great results. But for instance, already when the manifold is projective space, this moduli space is completely out of control. For P2, you're talking about plane cubics, which is classical but tricky. For P3, it's a paper in the Annals showing that there are 6 irreducible components of the moduli space. There's a paper in foliation theory. For P4, wide open, and one of the things that we did in our paper is to explain that there are lots and lots of components. Okay, so I'm going to do that by focusing on the local structure of M. Okay, in other words, I want to look at the deformation theory of a given log symplectic manifold. So by this I mean the formal or analytic neighborhood of this point in the moduli space. Okay. Maybe I'll skip giving a very formal definition for the talk, but you can define this as a formal deformation functor, or pick your favorite way of defining it, but you talk about families over a base in a manifold. Okay, so let me begin by reminding you what's known in the symplectic case, the local model for the moduli space. So, case where the divisor is empty. So this is the subject of Bovil, Bogomolov, Odorov theory, which I think we should also credit a little bit William Moser, who introduced the Moser trick in symplectic geometry for volume forms, which secretly is lurking in the background of these results. So the picture is the following. So we have the moduli space, which turns out to be smooth in this case. So we pick our favorite point. That gives us just an ordinary symplectic manifold, X omega, holomorphic symplectic. Draw it schematically like this. Okay. And now we want to understand what the nearby ones look like. Okay. So imagine taking a path to some nearby point, which gives me some xt and omega t. And, well, whenever we talk about families, we're going to require the family to be topologically locally trivial, which means that I can find some C infinity diffeomorphism, phi sub t, between these two manifolds. And then I can define a period map which works as follows. So because these manifolds are diffeomorphic, their second cohomologies are isomorphic by these maps phi t. And so I can take any point in the deformation space and produce a class in H2 of the central fiber by taking xt omega t to the class, which I get by pulling back omega along this map. Okay? And the basic fact, which is the local Torelli theorem for holomorphic symplectic manifolds, is that the period map is an immersion. Well, maybe let me say M is smooth near x omega. The period map is an immersion, and really it's injective. But the reason that it's injective is that if you had a compact scalar manifold, then this would decompose as the holomorphic 2 forms plus the 1-1 forms plus the 2-0 forms. Okay? And the period map somehow comes from deforming this part of the Hodge decomposition, but you never turn on a component in H2 of O. This corresponds to deformations where you add a gerb into the story. So if you want to get a period map which is an isomorphism rather than immersion, we have to look at a slightly more general problem, which is to include a gerb. Or another way of thinking about it is in terms of the generalized complex structures of Hitchin and Gualtieri. This is quite natural from the point of view of non-commutative geometry because those correspond to the full space of deformations, the derived category.
What is the target? Is it just the classifying space of these Hodge structures that you're connecting to?
I'm talking about the local problem. The target is H2 of x in this case.
Yeah, but you assign to it what precisely?
The cohomology class of omega. Remember, we're looking at not just x itself, but x with its 2 form. So if you only care about x itself, what you care about is the line which is generated by omega, and that's the Hodge decomposition of the cohomology. If you also want to remember the symplectic structure, you need not just that line, but an element in that line. So the correct thing is H2, not the space of Hodge structures.
It's a remark as a map going to the projectivization to
Okay, so just some intuition. Why is this statement true? Okay. Well, I've erased it already, but remember the Darboux theorem tells us that all holomorphic symplectic manifolds are locally isomorphic. Okay. So now, what does that mean? It means that X is locally rigid. If I try to deform it, the deformation will be trivial on a sufficiently small open set. So another way of thinking about the problem is that I have the local models and I want to glue them together by symmetries. Okay, but another thing is that there are not very many symmetries. All the symmetries are Hamiltonian, and the Hamiltonians are unique up to a constant. So when you work it all out, what you end up finding is that the deformation theory becomes totally topological. It's just controlled by the issue of patching together Hamiltonian vector fields up to a constant on a manifold. Okay. So that's the perspective which is going to be useful shortly. And it also explains why, in the case where the divisor is smooth, exactly the same thing happens. The only difference is now the period map from the deformation space to H2, it takes values not in H2 of x itself, but in H2 of the complement of the divisor. That's where omega has a well-defined cohomology class. Okay. But remember, we had this log version of the Darboux theorem, which says that everything is locally the same. So for essentially the same reason as this result, we get the
Darboux
Torelli.
theorem is only for one real symplectic form.
Pardon me?
The Darboux theorem is only for one real symplectic form. If you work in a holomorphic symplectic geometry, you have two real symplectic forms. So I don't see why you say
That's true. The Darboux theorem is about real symplectic forms, but the same proof works in the holomorphic category and gives you a holomorphic Darboux theorem with holomorphic coordinates.
with a fixed x.
Yeah, for fixed x, of course. Yeah.
Then you have the deformation of x.
Yeah, but the deformations of x you can think of as being given by taking opens in x and patching them together.
Structure with fixed x.
Thanks. Okay, so when D is singular, things become much more complicated. So now the moduli space ends up being singular itself. And the basic reason is that there are going to be deformations of x, d, and omega, where, for instance, the singularities of D change, and therefore the topology of the complement changes, and so H2 isn't constant anymore. So, what we did in our paper is to explain what happens under the assumption that D is a normal crossings divisor. Okay, to keep things simple, I will assume simple normal crossings in the talk, but our techniques are essentially local, so this doesn't really cause a major problem. The results hold more generally. So D is going to be a union of some components, Di, which are smooth, and meet as transversally as possible. And I'm going to follow the useful method of bookkeeping, which is to track the combinatorics of the intersection of all these divisors in a simplicial complex. Sometimes called the dual intersection complex. So this is a simplicial complex which has as its vertices, the chalk is wet, has as its vertices the irreducible components, okay? And then whenever two components intersect, I'm going to get a smooth subvariety of codimension 2, but it may have many irreducible components. And so if I take L inside of here, an irreducible component, I'm going to indicate that by taking the two vertices corresponding to the two components and connecting them by an edge which corresponds to L. So then a triangle corresponds to a component of a triple intersection, etc. So I'll call these components the strata.
Again, this still includes those examples with like the non-algebraic.
This includes exactly, so the toric
Yeah.
variety with this toric boundary fits into this example. It's completely irrelevant, actually, the foliations were transcendental. Although they are going to come, that fact somehow plays a role in the deformation theory secretly. Okay. So let me explain what these things look like locally. They're kind of similar to these toric examples. So you can think of this as the analog of the Darboux theorem for these normal crossing structures. So near a point P in X where exactly K components meet, this triple, x, d, and omega, is equivalent to a much simpler triple, which is a 2k dimensional affine space with coordinates x and y. The divisor is going to be the union of the coordinate hyperplanes in the x direction. The y's don't play a role for the divisor. And then omega has the following form. It looks like a sum of these dx over x wedge dy things that we saw in the log Darboux theorem. See, there are k poles corresponding to the k components in D. And then there's a deformation of this structure where you have something which is like those toric guys. Important distinction is that in the toric case, this had to be an invertible matrix, and we don't make that assumption here. Somehow this thing is already invertible enough to ensure that this whole expression is invertible.
Basically, here there is a stabilization.
I was about to say that, yeah, 1 second. So let me just first say what these coefficients are, and then I'll say why I wrote a squiggle instead of an isomorphism. Okay. So the bij's can be expressed as an iterated residue. See, if I take a residue when, say, xi is equal to 0, I'm left with bij dxj over xj. I take another residue, I get the constant bij. So this is the residue on xi equals 0, residue on xj equals 0 of omega, or if you like, more topologically, it's 1 over 2 pi times the square root of minus 1 squared, the integral over some little 2 torus of omega, where this is a 2 torus, which is somehow wrapping around the 2 irreducible components in the interior of
So is Bij here something that is depending on the other variables?
They're constants. This follows from the fact that omega is a closed 2 form. So for instance, these integrals will be independent of exactly how you choose the torus, or put differently, the residue commutes with D. So you have something which is closed and you take enough residues, you'll eventually get a constant function. Okay, so back to Mirko's question about this. So there's something a little weird here because this thing here has dimension 2n. And this here has a dimension k, which seems to depend on how many components are meeting at this point. Okay? And so what I mean here is not isomorphism, but a slightly more subtle notion of equivalence, which we call stable equivalence. So this is isomorphism up to symplectic factors. Okay, so I'm allowed on either side to add or subtract symplectic factors until I get such an isomorphism.
So is there then no normal form where you only add factors on the right, or?
Somehow, to get the cleanest normal form, which is this, you seem to need to add or remove. I can't really find a simple way of writing it. If I say fix the number of components and the dimension, then the simplest normal form somehow depends on the exact properties of this matrix. Yeah, it's a bit strange, but somehow the crucial thing is that deformation theory of Poisson structures is invariant under stable equivalence. And therefore, when we make our computations, we'll ultimately be able to reduce to this stable normal form a lot of the time, where things are much easier to calculate.
Dumb question. If I do a toric blow up, that's still, if I keep the same, formula for omega, that's still log symplectic?
Yeah, that's fine.
And are you identifying those two, or are you thinking of those as different?
I'm thinking of those as different, but yeah, I'm thinking of those as different. Because I'm always expanding at a point on the toric divisor. So when you make such a blow up, if you express it in local toric coordinates, the BIs somehow can look different, depending on exactly what you blew up.
And in general, is there some class of blow-ups that will preserve the log symplectic structure? Is there a natural way of saying that?
Yeah, so there's a nice proposition due to Polishchuk, which explains when you can blow up a Poisson subvariety. You have to look at the linearization of the Poisson structure in the directions transverse to the subvariety. And if it satisfies a certain property, then you can blow up. It's almost the same as requiring that the transverse linearization be 0, but not quite. But that's a very strong condition. Okay.
Even if you blow up some leaf, no?
Yeah.
No, it has to be
Yeah, leaves can have non-trivial transverse geometry. Okay, so I'm going to indicate these biresidues by, remember the codimension 2 strata correspond to edges in this dual complex. So whenever I have a stratum, I'm going to indicate its biresidue like this, just by labeling an edge with a number. But there's an important thing, which is that this depends on whether I did xi, xj, or xj, xi, because it's a skew-symmetric matrix. Okay? So I need to indicate an orientation of this edge when I do that. Okay, so anyway, these are constants, which depend only on which codimension 2 stratum you're looking at. And on the cohomology class of the 2 form. Okay, so what can we say about local deformation theory? So first of all, it was observed by Ram, not quite in this form, but what he proved is that if the biresidues are all 0, then this implies that all deformations are still normal crossings. We recover this as a consequence of our results. But something interesting already happens in dimension 2 when the biresidues are non-zero. Okay, so I could consider this very simple toric example, dx over x wedge dy over y. Okay? On the plane. So what's going on here? Well, I have the plane. The divisor is the union of the x-axis and the y-axis. And now it's very easy to deform this, because remember the 2 form being closed is an open, it's a vacuous condition in dimension 2. And a divisor being reduced is essentially an open condition. So I can do something like this. I can, for instance, change the constant. Okay. That's maybe not so interesting. But there's another thing which I can do, which is to take the divisor and smooth it out to get a hyperbola. Just by adding t to the equation. Okay. This is also a perfectly valid log symplectic structure. It now has a smooth divisor. Okay, and in fact, that's all you can ever do with this example. Locally, these are the only deformations. Everything looks like this. Okay. So our divisor D, which was D1 union D2, the two components somehow merged to get something which is irreducible. And so this suggests that in higher dimension, it would be interesting to take a log symplectic manifold and start trying to smooth out the codimension 2 intersections of divisor components. Let X be omega, the normal crossings, log symplectic manifold. And let L be codimension 2 stratum. So it's an irreducible component. Okay. We'll say that this stratum is smoothable if there exists a deformation of x, d, and omega, now a global deformation, that is locally of the form, well, I have L, and then in the transverse direction, I have this deformation right here. Okay, so the rough picture is that I have my stratum L, and L will have some normal crossings divisor, which comes from the remaining components of the divisor. Okay. And so generically, in the interior of this stratum, I have this picture of smoothing a node to a hyperbola. And now I want to globalize this. So it means I need to take this picture and I need to copy it in the transverse directions all along this stratum. Well, it will turn out, actually, that the space of deformations is somehow locally constant along L. And that's essentially because these are the only possibilities. And so there's a flat connection on the deformation space transverse to L, which means that you can take this deformation, and if you try to propagate it along a path, there's only one way to do it. Up to isomorphism. And so, for instance, now you have to worry what happens if I start by specifying the deformation at some point, and then I, for instance, go to the boundary. Could happen that the deformation blows up to infinity and you can't extend it. That's one thing that could go wrong. Another thing that could go wrong is that, well, this is a complex hypersurface, so I could make a loop around the divisor and come back to where I started. Because a local system, there's the possibility that, well, there's a unique way of continuing along this loop, and I may come back and get a different deformation from the one that I started with. And that's obviously also a problem. So there could be monodromy in the deformations. Okay, so one of the theorems that we proved is a characterization of which strata are smoothable. So L, corresponding to an edge in the dual complex, is smoothable if and only if the following three conditions hold. So first of all, there's a non-degeneracy condition, which is that the biresidue has to be non-zero, so that I can arrange this picture. The second condition has to do with what happens when I go into the boundary. I want to rule out the possibility of singularities on the boundary. It turns out that this is equivalent to the following conditions. So whenever I have a codimension 3 stratum, which remember corresponds to a triangle in the dual complex, I can label its biresidues. Like so I have to orient things. Okay? And then the condition is that for any such triangle, the following strange condition is satisfied. Bij plus bjk divided by bik is a non-negative integer. You can think of this, so locally near a boundary component there's some equation which is vanishing, and the deformation behaves like the equation raised to this power. So the only way it can be holomorphic is if the powers are a non-negative integer. Okay, and then the third condition has to do with the monodromy, and it says that for all loops, L inside of the open part of the stratum, there's a condition on the period of omega, so 2 pi square root of minus 1 squared bij, integral of omega over what I'm going to call Li minus Lj is an integer. And this Li minus Lj, each of them is a 2 torus, which I get by taking my loop and thickening it up to a torus which wraps around the component di or dj. But anyway, it's a topological condition. It only depends on the cohomology class of omega. All of these only depend on the cohomology class of omega. Okay, and consequently, the second cohomology of the complement carries an arrangement of linear subspaces which is given by these conditions on the periods.
Could you say again what this integral is over Li minus Lj?
Yeah, so, sorry, I was rushing because I'm short on time, but I have a loop in the stratum, okay? And then I also have 2 other components kicking around, di and dj. Okay? So what I do is I thicken this loop a little bit to make it into a 2 torus, which wraps around also di, but none of the other components. You can always do this by choosing a tubular neighborhood. It's this tube map. Okay, so since I'm out of time, let me do 2 things. First of all, I'm going to state a theorem, and then I'm going to show you some pictures. Okay. So the theorem is the following. This is the easy version of the theorem. This is what we call the non-resident case. So if these ratios, which appear here, are never negative integers, okay, this is what we call a non-resonant case. Then the deformation space of x, d, and omega is expressed as a union of linear spaces which have the property that when I, well, let me say it this way. The deformation space has a projection to H2 of x remove d, okay? And inside of this H2, I have this arrangement of linear subspaces, okay, which indicate when various strata are smoothable. And now the picture of the deformation space is that over one of these strata, there's an additional one-dimensional direction of deformations corresponding to those smoothings. And those can be done completely independently. So at the end of the day, what I get is a picture where I have this linear arrangement in H2, and over top of every stratum in the linear arrangement, there's a vector space whose dimension is exactly the number of smoothable strata corresponding to this point in H2. And I can go out in that direction. It gives me a different irreducible component of the moduli space, and that is the complete picture of the moduli space in a neighborhood at this point. So that's why I view it as an analog of the local Torelli theorem, because it expresses the deformation space completely in terms of H2. Okay, so if I could just quickly show you some pictures.
While we're waiting for it, or not,
So what is the picture again to the blackboard that you just closed, covered? So what are the structures of this? So you have this map from the deformation to the arrangement,
Yes.
and the fibers are?
They're vector spaces.
Yeah,
It's a constructible vector bundle.
Mm-hmm.
And the dimension of the fiber is the number of components in the arrangement that are
But
made.
you have this arrangement in the resonant or the non-resonant case, no matter what.
In the resonant case, it becomes more complicated. The fibers are no longer vector spaces. There are some singularities in the fibers, but we can write down monomial equations. Everything is written in terms of the period of omega, but the answer is much more complicated, which is why I didn't want to give it in the talk today. That's the last section of the paper. Okay, so here's a picture. This is the case where x is C4, okay? And the divisor is the first three components, okay? And the remaining direction doesn't have a component. And now I ask the question, how can I deform this? Well, there are going to be three residues that matter, B12, B23, and B31. Okay? So what I've drawn here is a projective space. It's a P2, which is the projectivization of the three-dimensional vector space spanned by the biresidues. This is the H2 of the complement. Okay, the dashed lines going forming a triangle, those correspond to where one of the three biresidues is 0. And the gray lines, which are parallel to those dashed lines, those are the locus where that corresponding stratum is smoothable. Remember, there was this parameter, this ratio here, right? So I have to specify a non-negative integer. Every time I do, it gives me a line. So I get actually a countable collection of these gray lines, one for each of the three biresidues. Okay? Now, if I'm at a generic point, there are no lines, nothing is smoothable, the deformations remain the same, like all I can do is change the b's. But if I go on to one of the gray lines, I can smooth the stratum out, so the moduli space has another irreducible component which sticks out here with one extra dimension. Still smooth, that component. Okay, and now I can go where two intersect. And then that means I can smooth out 2, and there's a two-dimensional space sitting on top of it. And then, interestingly, there are a finite number of triple points. And those are quite special. They correspond to deformations where the divisor becomes an elliptic singularity. And then there are also these red ones. These are the resonant case. And what happens there is if I smooth out two of the lines, smooth out two of the components, then actually the third one automatically gets smoothed at higher order in deformation theory. That's why it's so much more complicated. That's where the singularities in the moduli space get introduced. Anyway, you can completely write down everything very explicitly. You can write equations for the divisor and everything. You get some classical familiar singularities.